Hello, it's Keith here, and this is the third of the platform-specific series of my PDP-11 programming tutorials. We're back on the UKNC today. That's the Russian PDP-11 based home educational computer, and we're going to be looking at graphics again. Now, last time we looked at getting 4-color graphics 2-bit planes onto the screen, and that's pretty easy because we can use the so-called wrap device, which is a port-based system that allows us to access the full memory of the system within limits from the main CPU. And I say within limits because the limit is that the main CPU can only access 2 of the banks of memory and effectively 2 of the bit planes. However, we can use the so-called peripheral processor, which I tend to refer to as the sub-CPU, which is the second CPU which handles things like the keyboard and is designed for the graphics and sound and things, and that via the wrap device can access all 3 bit planes. And so that means we can access the 3 banks, and we can change the color to any one of the 8 colors that the system can use. Now, by default, these are the sort of primaries. That's black, red, green, blue, cyan, magenta, yellow, and white. And so we can do quite a nice Chibico, as you can see up there, and we can see it just here. There's our Chibico character that we're going to be drawing today. So we're doing this via the sub-CPU, and so what this means is we have to program the main CPU to send a command and some data to the sub-CPU to execute, because we can't write a program straight on the sub-CPU. We write it on the main CPU and transfer it across. And so then we tell the sub-CPU to run that program, and the program we've transferred is the Chibico bitmap and the code to transfer that Chibico bitmap into VRAM. So that will show the graphic. Now today we're going to be looking at the default layout of the memory, because you can remap it via a line table, but we're not going to do that today. So today we're just going to be using the system as it's configured with the default colors and the default memory layout. But it's more important what we're seeing today. The more important thing that we're seeing today is how to configure data to be transferred to the sub-CPU and executed, because once you know how to do that, you can do other things like, make the sub-CPU reconfigure the line table, which is in sub-CPU RAM and things like that. So I think it's a really interesting lesson today. And to be honest, having programmed other systems like the FM7, which uses multiple CPUs, the procedure is often very similar. There's a sort of set of rules. You have to create a command, if you can call it that, a set of bytes that are in the correct format that the ROM of the sub-CPU will expect. The ROM will then take those bytes, it will then read in whatever program you've given it, and then once your program is running, you're then totally in control if you wish to be, and you can either disable the original ROM or just never get back to it and just do all of your own stuff from there on, or you can do a little task like we did today, draw the Chibico and then return, and that's the other way of doing things. But it all comes down to you need to know how to do this, make the sub-CPU do what you want, and that's what we're going to be looking at today. So let's go over to the code and let's take a look. So here is what we've got today. Now I have to say a very big thanks to Aberrant Hacker here, who provided me with a lot of my UKNC resources, because all of the documentation is in Russian and Google Translate didn't help much. It did a good job, but technical documentation a few words out here and there, and it stopped making any sense. So he was very kind of to provide me with some source code samples and things that are the basis for today's lesson. So while I've made a few tweaks and things, I really wouldn't have been possible without him, so thank you very much there. Okay, so today we're going to be going over this example, and the code that our main loop is just transfer this data to the sub-CPU and run it, and then just stick in an infinite loop. So the sub-CPU is doing most of the work today. Now we have our bitmap, as we saw just a moment ago. We are going to be including that as byte data here. You can see all of the lines here. Now there's 3 bit planes, and of course each byte will contain 1 bit plane, and it will contain 8 pixels. So there's going to be 3 bytes per a cluster of 8 pixels, and I've split this into 48 lines because the sprite is 48 by 48. Now if you wish to create your own sprite, you can always do so with my AccuraSprite editor, because my AccuraSprite editor supports absolutely every system I've covered in my tutorials. All you do is you go to the PDP-11 option here and you select UKNC, and then you've got options here for save raw bitmap, 2-bit planes, 3-bit planes and 1-bit plane. The 1-bit plane we'll use later on. Today's example is a full 3-bit plane option, so that's what you want to use to create the file in the correct format, and then you just paste the byte data that's output from that into here, and that's our sprite. Now we've got our program here, which is what we're actually going to get sent to the sub CPU, and that will actually create the sprite. We will be looking at that in a moment, but for now I just want to point out that we've got this routine called show. It's a very short name because of the 6-character limit. Any more than 6 characters in a label name is ignored. And show E, represents the end of the show command, and show represents the start. Now the other thing to notice is all of these are relative branches and things here. This is a relative branch to here, so it's done as an offset, not as an absolute address. And here we're calculating the sprite location. We're subtracting the current location in the code here and then adding it to the program counter here. And the reason for this is that these are all, the show as it's represented here will be an address in the main CPU, but this will all be transferred to somewhere, we don't know where, in the sub CPU and then executed. So all of the addresses will change. So branch commands are going to be fine because this is a relative command, so that's fine. Return command is fine, of course, and this is being recalculated based on the program counter, so that will work as well, but we can't use any absolute addresses in here because they won't work anymore. Okay, so that's the sort of command we've got, and what we've done here is we are loading the start of the command into R2, the end of the command into R3, and then we're using this send command function, which I've sort of tweaked. This is based on the code that I was provided with, so this is all pretty much as is. I've just made a few slight changes just to make it a bit more the format that I wanted to work with, so to speak. So when we want to get the sub CPU to do something, we have to send it the data that it's going to expect in the format that the ROM will want. And what we do is we pass some bytes, and we pass them in this format here. So we pass these bytes initially, and these contain a pointer to a series of bytes here, which are the command that we want to run. So we're going to use multiple commands this time, but rather than have multiple structures, we're actually just going to tweak certain parts of this one. So for example, PS request here will be a 1, a 2, a 10, 20 or 30, depending on which of these commands we want to run. And then the arguments will be passed and returned relative to those commands, so they will change depending on the command. Now this piece here, we don't change at all. This is just a pointer saying, hey sub CPU, I've got a command for you, here it is, get on with it. And then sub CPU will read this in, and then it will process it. So that's this is our sort of template that we're going to tweak later on to actually work with our commands. Now our sub CPU will be working away and can work away while our main CPU is doing other things, but for the example today, the main CPU is actually going to stop until the sub CPU is finished. And the way we detect if the sub CPU is finished is we've got a flag in the main CPU's RAM. And this will be a 0 when we start, and then we will wait for it to change, and the sub CPU's program will change it. And so our main CPU will wait until this changes, and it will be changed by the last command of the command we've passed to the sub CPU here. And what this is doing, and we'll discuss again later, is it's calculating the address in main RAM that it needs to pass to the wrap device, and the wrap device has access to all 3 banks of RAM, including the main CPU's RAM from the sub CPU. It only has access to 2 banks of RAM from the main CPU. So the main CPU cannot change the sub CPU's RAM, but the sub CPU can change the main CPU's RAM. And so that's what it's doing. Our program will finish by changing this to a -1, and so our send command will wait until that changes to a -1, and when it does, then it knows the sub CPU has finished. That's how we'll detect that. So that's not actually part of the command being passed. That's just a variable that we need for our purposes. So we're running our send command, and we are passing R2 as the start of the command and R3 as the end of the command. And the first thing we want to do is calculate the length of the command, and we want to calculate it in words. So what we're doing here is we are taking the end of the command here, the memory address of that, into R4. We're then subtracting R2. We've now got the length in bytes. We then shift it to the right once, and now we've got the length in words, and we're going to want that later on. Okay, so what we do next is we want to actually send a command to the sub CPU, and what we want is we want to tell the sub CPU to give us some memory for our command. So we are going to use command 1. So we're moving that byte into PS request, and you can see that just here. So we're altering this byte in memory to be one of these commands, in this case command 1, and then we are transferring the amount of bytes we want that we just calculated here, and we are sending that to the sub CPU with this PPU out command. Now PP, I believe, stands for Peripheral Processor. I'm not quite sure what the U stands for. Peripheral Processing Unit maybe, I'm not sure. I'll have to maybe guess that, but anyway, that's the command we're using here. So we're then taking our parameter value here, and this is a pointer to up here. So this is the parameters. So this is just a pointer to the structure with some sequences here, which I guess are required by the ROM. I don't have any real documentation on that. I do have some disassemblies of the ROM, but I haven't looked at them. So this is as is, we never change this, and this is the command we're passing to the sub CPU. So we are defining the size, which is always 8 bytes. We are transferring all of the bytes to this port here, 177676 here, and we're then waiting for each byte to be received, and we're just repeating until all the bytes have been sent. We then test the reply, and this is the status code of whether the command succeeded or failed, and we might want to respond to that, because obviously if our attempt to request memory failed, well, we can't carry on really, so we're jumping to the error routine, and the error routine actually in this example just abandons and stops our program there. So that's what we're doing if things go wrong here. Okay, so we've now got some memory, and the PPU command will actually alter the parameters. The parameters when we pass them have one function, but in this case when they return they have another function, and argument 1 now contains the address of the memory that's been allocated. So we've got that, and we're now going to store it, and we're going to store that in R5. I changed that slightly from the code I was given. The original code was storing it in another RAM variable, but I thought we'd just save it in a register to save a little bit of memory. So that's what we're doing there, saving it in R5. So now what we're going to do is we're going to transfer our program. So we've got our program's start in R2 and our program length in R4, and we're storing those in variables A2 and A3, and this time we're going to use command 20 as the command we want to run, and this is copy from CPU RAM to the PPU RAM. So we're going to transfer our program over. So we just use that PPU out command again. In this time, this will transfer our program. This will tell the sub CPU to do some work, the work being transferred to the program, and then it will transfer. So that's what we're doing there. And we wait, and again, if there's an error, then we need to know about that, so we give up in that case. Now our program has been transferred to the sub CPU, so this time what we're going to do is send the command execute. So we're changing the command to number 30 here, and then we are calling PPU out again, and that is telling the PPU to execute that command. And then what we're doing next again is we're checking if there's an error, but then what we're doing is we've got to wait, and we're testing the flag end to see if it's 0. Now we actually zeroed that at the start here, so it will start as 0, but it will not change until our program actually completes, because as I said before, the last command of our program is moving a -1 to flag end. So it will, if our program finishes okay, reach a -1, and then it will finish. So when that finishes, the wait PP ends, and we've then got another command. This time we're using command 2, which is free memory, and we're releasing the memory and the length of the memory that we were allocated. So we're setting those parameters there, command number 2 this time. We're running PPU out again to free the memory, and then we're returning, and if there's an error, we're going to the error routine. So in this case, in this simple example, we're just doing one command. We've just got this one command here, which is the show Chibico command. Next time, though, we're going to have a look at a program with multiple commands. We're going to do potentially 2 commands, because we're going to use a line table. We're going to configure the VRAM to be different and change the screen resolution and things, and then we're going to potentially run a sub program on the sub CPU that will show a sprite on that system as well. So this routine does indeed work for multiple commands, even though in this case we're just using it for one. So that's how we send a program to the sub CPU and execute it. What about the command we're actually executing? Well, it's pretty straightforward. So the first thing we're doing here is we are calculating the memory address of the sprite relative to the program counter. Sprite minus dot, in this case the dot means the current program counter address. So what this is calculating is the offset in the code from the current line of code here to the sprite which is down here. And the reason we're doing this, as I say, is because these absolute addresses show in sprite won't be the same on the sub CPU. So we're calculating them here relative to the program counter and adding the program counter at the point that this code is running on the sub CPU. So then we've got the valid sprite address again. Now the VRAM is effectively from memory address 1 and 5 zeros in octal. So this is a few lines down. You could, if we just change this here, we could have 00000 here. And if we run this again, Well, now our Chibico is right at the top corner of the screen there. So as I say, that's basically the start of VRAM, and we can change that value there to offset our sprite into different positions on the screen if we wish. So we're moving that into R1 as the VRAM address of the start of the sprite. We transfer that to 177010, which is the VRAM address port, and that's effectively this wrap device that allows access to all of the system memory from the sub CPU. So we're selecting the address we want to write to, and this address is the start of VRAM. And then what we're going to do is we're going to transfer all the bytes of the lines, all 48 of them. That's why we've got 48 here, and 6 bytes per line, 3-bit planes per byte, or 3-bit planes per cluster of 8 pixels, so 6 clusters of 8 pixels. So that's what we got, and 48 is in decimal this time. There's a dot at the end, that means decimal. So what we've got to do is we've got to transfer all 3-bit planes, and we need to use 3 different ports of the wrap to do this, the wrap being the memory address device, and we're writing in this case. So 177012 is plane 0, which in this case is blue. 177014 is the green bit plane, plane 1, and 177015 is the red bit plane, plane 2. Now I say that I'm referring to the planes as usually blue, green and red and things, because you can reconfigure all the colours if you wish. So this is the default colours, but you could swap all those around, or you could change them to different combinations, like you can have cyans, dark cyans and things if you prefer. So that's the default colours, but that's not to say that's what they need to be. So we've now set all 3-bit planes for 1 cluster of 8 pixels. What we do next is we move along 1 byte by incrementing the wrap address port there. So that moves us along 1 byte of the screen. We then repeat until we've done all 6 bytes of the line. When we've done a whole line, we're then adding 80 bytes in decimal. That dot at the end of the 80 means decimal, minus 6 to the minus 6, because we've just written 6 bytes to the wrap port there, and that will move us effectively down a line. We then repeat until we've done all of the lines there. Once we've done that, we've finished. So we want to set that flag to tell the main CPU that we've finished. Now what we're doing here is we're taking the address of flag end and dividing it by 2. Now the addresses in main memory are split between 2 banks of memory, and they're actually alternating bytes. So alternating bytes are bank 0 or bank 1. So the 64K of main CPU memory is the first 32K of the first 2 banks of memory, and so the address that we need to give the wrap to write to the memory is actually half of the address that we would be accessing in main CPU RAM. So the main CPU RAM address is flag end, and so the address we need to give the wrap is flag end divided by 2. We then write the -1 to that to port 177014, but we're specifying a 16-bit write there, so it will actually write to 177014 and 015, which is the alternate bank. So we'll be writing to banks 1 and 2 at the same time there. So they will both be set to -1. That's why we used a 16-bit value when we defined flag end. And so there we go. So that's what we need to do to get our Chibico onto the screen. As I say, I mean, the code that does the transfer is sort of identical to the last one. The last one we did all this from the main CPU, and the disadvantage of that was we could only do 2-bit planes, and now we can do all 3. But the code is very, very similar. As I say, the main thing that we've really seen and we've gained from this is that we've now got some sample code that we can use to send commands to the sub CPU and get that sub CPU doing some work for us. And there's going to be things later on that we will want to do that will make our lives a lot better, because we can reconfigure the graphics. We can change the screen from a 80 character widescreen to a 41. We can have more of like a 320 by 240 style screen, which is what I prefer. We can reconfigure the colors, and we can also reconfigure the video memory, because at the moment the video memory is outside of the memory range that is directly addressable from either the main CPU or the sub CPU, which means we have to use that wrap device to write to our memory. But we can actually remap the memory, and we can have it much lower, and that means if we only need 4 colors, we can actually map the video memory to the addressable range of the main CPU, and we can just leave that sub CPU for less important stuff like music and things. So we can reconfigure that, and that's what we're going to be looking at next time. So say really it's a fascinating system, and I find the multi-CPU thing a little bit difficult in some ways because it's always a lot harder to get started, but it is, from an educational and from a challenge point of view, it's really quite fascinating to see how these systems interact with their different CPUs. And in this case, they've made some really interesting choices with the memory mapping that, while surprising, are actually very beneficial because of the flexibility that it gives you. Most of the time, the sub CPU can't write to the main CPU RAM at all, really, without halting the main CPU. And as I say, in this case, we've got the flexibility of having the video memory outside of our normal range, or we can alternatively sacrifice some of the addressable range and have it within that range. And say we can have eight colors, or we can sacrifice down to 4 colors, and we've got lots of choices here that are available to us because of the flexibility of the system. So I think it's really good. Anyway, I hope you've enjoyed this today. If you have, please hit the like button and please subscribe because, as I say, I've got more content coming and you will probably want to see that. So that would really help me out. But anyway, as always, you can go to my website and download the source code and the build scripts and all that fun stuff and have a go with it yourself, because that's what this is here for. It's not here for you to just watch. You should be downloading it and trying it out. And as I say, please do whatever you can with it. I mean, the scripts that I'm using today are ones that I found on the internet, the source code. So, you're welcome to do anything you want with it as well. I'm sure all of the UKNC fans would be very happy if people started experimenting and creating new stuff for their system. I'm sure they'd love to see that. So I'm sure they'd welcome it. Anyway, thanks for watching today and goodbye.